Hello. In this video, we will go over diagonalization for linear algebra. So this is linear algebra diagonalization. So the matrix D is a diagonal matrix. Um, Basically, entries off the main diagonals are all zeros, making D raised to the K easy to calculate. So if you have a diagonal where here I'll show you an example what they mean. So let's say you had this matrix D, this 2 by 2 matrix, right? 5, 0, 0, 4. Notice how how these are all zeros. That's a good thing. It's easy to find d squared or d cubed and dk. So if they wanted you to find d squared, you could do the long way, multiply these two matrix, but basically you're squaring the diagonal. So d squared is 25 squared and 16 squared. And then if you wanted d cubed, you would just have to cube the diagonals, right? So this is going to be 5 cubed, 4 cubed. You could do the long way, but really you don't have to because so the keynote is if you have these all zeros, that's good. So d cubed would be this matrix. But what happens if you don't have the zeros below if you don't have the zeros or if it's not a diagonal? For example, if this matrix 5, 3, 1, 4, this 2 by 2 matrix, and they want to find the A20th, what do you do? So let's talk about the procedure for diagonalizing a matrix. Okay, so go ahead and write this down in your notes. So step one, solve the characteristics equation to find the eigenvalues lambda 1, lambda 2, and lambda n. What does that mean? I'll show you an example. Just write down the notes. And then step two, find the corresponding eigenvectors. Step three, form matrix P, or matrix P having as its columns. Step four, form the matrix D with lambda 1, lambda 2, lambda n on the diagonal corresponding to the same order as P1, P2, Pn. Step five, check that A equals P times D times P inverse. P represents the eigenvector, D represents the eigenvalues. Note, A raised to the K is P D raised to the K times P to the -1. Fact, square matrix A is diagonalizable. I can't say the word. Diagonalizable if A equals P times T. If A equals P times D times P inverse, where P is invertible and D is a diagonal matrix. Okay, so diagonalization theorem. An n by n matrix A is diagonalizable if and only if A had the n linearly independent eigenvectors. Thus independent eigenvectors, thus any n by n matrix with n distinct eigenvalues is diagonalizable. So let's do an example where it's not where you have a matrix that isn't diagonal isn't a diagonal. So let's say you have matrix A, this 2 by 2 matrix, 6, 2, -1, 3. Find A20. So how do we do this? So yeah, let's go over this problem. So step one, well, did you know that I do know, what do we know? I know that A20 is the same thing as P times D raised to the 20 times P inverse. Okay, so first step, what I'm going to do is find the determinant of this 2 by 2 matrix. So how do you find the determinant? Uh, So it's going to be 6 minus lambda, and then 2 stays the same, and then -1 stays the same, and then 3 is now 3 minus lambda, right? Equals to 0. And then find the determinant of this 2 by 2 matrix. It's easy for a 2 by 2, right? You just multiply the major minus minor. So it's really 6 minus lambda times 3 minus lambda minus bracket 2 times -1. And then when you FOIL this out, 6 times 3 is 18. 6 times -x is -6x. I mean, -6 lambda. Negative lambda times 3 is -3 lambda. Negative lambda times lambda, negative lambda times negative lambda is lambda squared. And then 2 times -1 is -2. And then you have an extra minus, so that becomes +2, right? And you set that to 0. Now go ahead and solve for lambda, so you're going to have to factor. So let's put this in order. So it's going to be lambda squared. -6 lambda minus 3 lambda is -9 lambda plus 20 equals to 0. And then go ahead and factor this out. So this is going to be lambda -5 minus 4. Okay, so now we found our lambda, and our lambdas are lambda equals 5 and lambda equals 4. And yeah, so what this means is we have eigenvalues and two distinct eigenvalues. Okay, so let's do another example. Oh wait, no, sorry. Uh, we're still on this problem. So we got to find what's the next step? We got to find the eigenvectors. So we basically got to find P, right? Because if we know we're going to use this formula right here, we got to find P. Okay, so how do we do that? Okay, so step 2, find the eigenvectors. So if P equals A minus lambda identity augmented with 0, um, that's the same thing as A minus lambda I equals to 6 minus lambda 2, and then 3 minus lambda, and then this is still -1, augmented with 0. So all we get, it's the same thing as, it's almost the same thing as step 1, finding the determinant. All we got to do is augment it to 0. And then what we're going to do next is we're going to row reduce when lambda, let's try, remember how we have two different lambdas? Let's try it when lambda equals 5. So if lambda equals 5, that's going to give you 6 minus 5 is 1. This is 2. This is -1. 3 minus 5 is -2. Augmented with 0. So when you row reduce, maybe I want to get this 2 into a 0. Um, I'm just going to put that in the calculator because we don't You could just simply put this in the calculator. This is what you're going to get. 1, -1, 0, 0, augmented with 0, 0, right? And this is column x1, this is column x2, right? So this is going to be x1 minus 1 x2 equals to 0. So when you actually solve for x1, you're going to add 1 x2. So you get x1 equals to x2. We also know x2 equals x2. So that gives you 1 and 1. Okay, now let's do the same process when lambda equals 4. You get 2. So 6 minus 4 is 2. This is 2, -1. And then 3 minus 4 is -1. And then we're going to augment it with 0. And then when I do my row reduce, you could just put that in the calculator. I get this. 1, -1/2, 0, 0, augmented with 0, 0. So this is column x1, this is column x2. So when you solve for x1, we're going to get 1/2 x2. And when you solve for x2, you're going to get x2, right? So now you get, so this is 1/2, 1. Or if you want to factor out a 1/2, this is going to be 1 to 2. Okay, now step 3, we got to find P. So P is basically our vectors. Our vectors. So step 3, our P is going to be, so our first vector was 1, 1. And then my second vector was 1/2, 1. Step 4, find D. So D is D. Oh, D is basically, what is D? Your lambda value. So D is going to be, our lambda was 5 and 4, and so you just make the others 0, the diagonal 0. So step 4, our D is the lambda. One of my lambda was 5, and my other lambda was 4. And then you make these zeros. Step 5, put it in the formula. So we now know our P, we now know our D20, and I believe we also know our inverse. Okay, so it's going to be A20 equals, my P was 1, 1, 1, 2. My D20 is basically, so D20 is basically, oops, this raised to the, just raise it to the 20. So what's 5 raised to the 20? Hmm, I guess you could say 520. I don't I don't want to write it out because it'd be very large. Yeah, 5 raised to the 20. Yeah, it's a very large number, so we're just going to leave it as 520. This is 0, this is 0, and this is 420. 4 raised to the 20. So this is going to be 5 raised to the 20, 0, 0, and then this is 4 raised to the 20. And the last one was our P inverse. Our P inverse, we know our P is this, so our P inverse was, you could just put it in the, so that, our P is this, and then my P inverse, you could just put that in the calculator. You get 2, -1, -1, 1, right? Okay, so this is your, when you multiply it out, you could just leave it like this because it'll be a matrix, but this is fine. So this is A20. Okay, let's move on to next example. Okay, so this example says let A equals this 3 by 3 matrix. Find matrices, find matrices P, D such that A equals PD times P inverse. So it's just like the first one, but they just want you to find A, not a certain power. So basically we got to find matrices. Yeah, so step one, I'm going to do is find the determinant of this unfortunately 3 by 3 matrix. So how do you find the determinant of a 3 by you're going to have to need to use the cofactor and Cramer's rules, right? So you're going to set it up like this. It's going to be 2 minus lambda, 1/2 stays the same, 0, 0, and then 3 minus lambda, 0, 0, 1, and then 2 minus lambda, right? Equals to 0. And then if you recall, my cofactors, so this number is going to be plus, negative, plus, minus, plus, minus, plus, minus, plus. Okay, so now what I'm going to do is, I think I'm going to use, you can use any one you like. I'm going to use this row because it has a lot of zeros. And remember when I like zeros because anything times 0 is 0. So I'm going to use this row. So it's going to be, so this one is a positive. So it's going to be 2 minus lambda, and then create your 2 matrix. It's going to be, so imagine this, removing this row and this column, you're left with 3 minus lambda, 1, 0, 2 minus lambda, right? So all I'm doing is ignoring this row and then this column, and then this is what I get. Okay, and then it's going to be minus 0, and I don't even care because anything times 0 is 0, and then it's going to be plus 0, and I don't really care because anything times 0 is 0, right? So really it's just this part that we're concerned. This just all becomes 0, right? Okay, so what you do is now you're just gonna, you know how to, this is easy to take the determinant of a 2 by 2, so it's going to be set up like 2 minus lambda bracket, and then it's going to be 3 minus lambda times 2 minus lambda minus 0, or 1 times 0 is really 0, right? Equals to 0. Okay, so now you have 2 minus lambda. You do not have to FOIL it out. Instead, just write out your 2 parentheses. And you could solve for lambda by setting each equation to 0. That's perfectly fine. So if you set 2 minus lambda equals 0, 3 minus lambda equals 0, and then 2 minus lambda equals 0, right? And when you solve for lambda, you're going to get 2, 2, and 3. Okay? We have 3 eigenvalues, but we need 3 eigenvectors. So let me write that down. We have 3 eigenvalues, 3 eigenvalues. but we need three eigenvectors. Okay, step two. Now we're going to solve for p, so it's going to be p equals a minus lambda I augmented with 0. So let's figure out, let's do when our lambda is 2. So this would be um 2 minus 2 is 0. So it's really saying 2 minus lambda 0, 0, 1 half, 3 minus lambda 1, 0, 0, 2 minus lambda augmented with 0. Okay, so when you do that, you're going to get this. 0, 1 half, 0, 0, 1, 0, 0, 1, 0, augmented with 0, 0, 0. Okay, so when you row reduce, because I'm going to just do an algebra. Yeah, when I row reduce, I get this. 1, 0, 0, 2, 0, 0, 2, 0, 0, augmented with 0, 0, 0. Okay, so this is my x1, x2, x3. So okay, so this is going to be x1 plus 2x2 plus 2x3 equals 0. And then when you solve for x1, you get x1 equals to negative 2, x2 minus 2x3, x2 equals to x2, and then x3 is equal to x3. And then, so we get this matrix x2, negative 2, 1, 0, plus x3, negative 2, 0, 1. Okay, so now we're gonna do the same process for when lambda is equal. Do the same process when lambda equals to 3, or lambda equals 3. You're gonna get this 2 minus 3, 1 half, 0, 0, 3 minus 3, 0, 0, 1, and then 2 minus 3. And we do the work. You're gonna get this negative 1, 1 half, 0, 0, 0, 0, 0, 1, negative 1, augmented with 0, 0, 0. And then what you want to do is row reduce. When you row reduce, you get this. And you get x1 equals to 0, x3 equals 0, and then x2 equals x2, right? You get this vector, basically 1, 0, 1, 0. Okay, so my eigenvectors is equal to -2, 1, 0, -2, 0, 1, and then 0, 1, 0. Okay, so find my eigenvectors. Now, step 3, we got to find our p. So our p is okay, step 3. Okay, step 3, our p was p equals to the matrix -2, 1, 0, -2, 0, 1, 0, 1, 0. And then our d was when you make the diagonal zeros. So our d is our lambda. So our lambda was 2, 2, and 3, right? And then you make everything else 0. My d is going to be 2, 0, 0, 0, 2, 0, 0, 0, 3. Okay, step 5. My a is going to be p, d, p inverse. So it's basically this matrix. So a is going to equal to -2, 1, 0, -2, 0, 1, 0, 1, 0. And then this is going to be 2, 0, 0, 0, 2, 0, 0, 0, 3. And my P inverse was, so my P was this. So the P inverse, if you could just use the calculator, that's fine. You get -2, 1, 0, -2, 0, 1, 0, 1, 0, right? Okay, that's step 5. Okay, let's do another one. So So this example, by inspection, determine if the given matrix is diagonalizable. So this is a 3 by 3 matrix, and what do you see that's so specific about this? These are all zeros. So you form like a triangular, right? Uh, so that means if you have a triangular diagonal, if you have a triangular, yes, or yeah, if you have a triangular diagonalizable, I mean a triangular matrix, meaning you have like zeros here or zeros here. Uh, yes, it is diagonalizable, and that means our lambda is going to be the diagonals, 2, 6, 1. So this one's not too, this was an easy one. I wish all our problems were diagonalizable. That'd be easy, but they're not. So we have three distinct eigenvalues. So we have, so we must have three distinct eigenvectors. Three. So we must have three distinct eigenvectors. So yes, diagonalizable. Okay. Oh, there's a part B. So part B, you have this A equals this matrix A equals 2, 1, 0, 2. Because you have a zero here, that means our lambda is going to be 2 and 2. So we have a when you have a multiplicity, it's not guaranteed a diagonalization. So because of we have a repeat of 2, right? We have a repeat of 2 or a multiplicity or multiplicity. Uh, we are not guaranteed diagonalization. So not diagonalizable. If you have a 3 by 3 matrix, if you have a 3 by 3 matrix, you can have one pivot and two free variables. So let me write this out. If you have a 3 by 3 matrix, you can have one pivot and two free variables. But for a 2 by 2 matrix, for a 2 by 2 matrix, one pivot, at most one free variable. Okay. Well, and then the last thing we want to go over is di this diagonalization theorem or a continuation. Okay, so diagonalization theorem continued. So let A be an n by 2 matrix whose distinct eigenvalues is lambda 1, lambda 2, lambda lambda p. So the first part says for one, whoops. So for the first part says for k's between p and 1, the dimensions of the eigenspace for lambda x is less than or equal to the multiplicity of the eigen lambda k. And then the second part, part B, says the matrix A is diagonalizable if and only if the sum of the dimensions of the distinct eigenspace equals n, and this happens if and only if the dimensions of the eigenspace for each lambda k equals a multiplicity of lambda k. And then this third part, C, if A is diagonalizable eigenvectors and linearly independent, and Bk is a basis for the eigenspace corresponding to lambda k, for each k, then the total collection of vectors in the sets of B1 to Bp forms an eigenvector basis for Rn. So for example, you have the lambda equals 1, 3, 3, 2, 2, 2. We have a 6 by 6 matrix because we have 6 lambdas, and you have a repeat of 3 and a repeat of 2. So we have a 6 by 6 matrix that we have a 6 by 6 matrix and we have 6 eigenvalues. That means we better have 6 eigenvectors. 2 eigenvectors when lambda equals 3 because we have a repeat, and 3 eigenvectors when lambda equals 2 because you have a repeat of 2. So that means lambda equals 1 is one eigenvector because, yeah. So when lambda equals 1, you have one eigenvector, and when lambda equals 3, at most 2 eigenvectors. And when lambda equals 3, at most 3 eigenvectors. Okay, so that is linear algebra diagonalization. We will stop here, and then we will talk about next video should be about eigenvectors and linear transformation.